All right. So last time we introduced sort of really some key concepts for second order or for circuits in general, AC circuits. Let me pull up. All right. All right. So we talked about some key concepts as it relates to sinusoidal circuits, right? So basically what I said is, sine waves happen a lot in electrical computer engineering problems, okay? Many real signals that are processed by circuits are sine waves. Audio signals, power, radio. Gave those examples. We talked about those. All right, so they're pretty common, and they're very special. And I guess I said in general, if I had to describe quickly, what's the difference between DC versus AC? What is the difference between the two?
AC changes its magnitude and DC does not.
Yeah, DC basically, as a function of time, stays constant, right? So if I watch on an oscilloscope a DC waveform, I see a constant value. AC, yeah, I'm seeing it kind of change its value over time. And the good thing about any AC waveform is I can think of any AC waveform as being a sum of sine waves, even if it's a square wave, right? We said even a square wave is a sine wave, and that's a pretty common type of waveform. Or a square wave is not a sine wave, but a square wave is a sum of sine waves. So I think, for now, it's suffice it to say that that's probably enough for you guys to know.
I think it's him. I see everything else.
Okay.
What's up?
I think you kind of lagged there a little bit, and I wasn't sure. My Wi-Fi sucks, so I thought it was me. Just want to make sure.
Yeah, I mean, I think hopefully it's not mine. I've got the university's. Hopefully it's good, but it may suck.
It went red for a second.
Okay.
You're fine now.
All right. Well, I probably didn't say anything all that useful anyway, but if I had a square wave, I can think of a square wave as a sum of sine waves. Sine waves have a really special place for us. And so we've got all sorts of useful tools for dealing with that. So today we're going to deal with one of those tools, which is this idea of what we call impedance, okay? All right, it's going to allow us to get rid of differential equations, and that's kind of the key thing for us. All right, so last time we started looking at sinusoidal sources, and we basically said, I said there's two types of circuits. A static circuit where I only have resistors, and a dynamic circuit where I've got inductors and capacitors. And in cases where I have inductors and capacitors, what's the big difference? From your perspective, when you need to sit down and you need to do circuit analysis, what's the difference between a circuit with resistors and a circuit with R's, L's, and C's?
The amount of time it takes to solve it.
Yeah, amount of time it takes, differential equations. Both of you guys said the right thing. You may think circuits 1 is a pain in the butt, but all the stuff you've done up till now really is a pain in the ass, right? No one wants to deal with differential equations every time you have to go about solving a problem, right? And that's kind of the key issue. But if I have a circuit with R's, L's, and C's, or if I have any time I have a differential equation, so anytime I have d, v, c, dt, whatever, dil, dt, all that stuff. Anytime I have those, I'm going to have two components to my solution, right? What are the two components we said we have?
Transient, steady state.
Yep, transient and steady state. And somebody else, I heard the words particular.
And homogeneous, yeah.
Yeah. So steady state means after the transient. This in the math world, they'll call this particular. Engineering context, we usually more say steady state, and this guy's the homogeneous. Okay, so it's those two responses that we have. What's true about transient? Always
goes to zero.
Goes to zero, and in general, it's always a e to the st. Always, even if it's second order. It may just be that S is complex, and so I get sine waves that come out of it, but there's always an AE to the ST. It always goes to zero. Always goes to zero. Okay? So bottom line is, if it always goes to zero, why do we care about it? And it turns out sometimes we care about it when we care about it, and we don't care about it when we don't care about it. And most of the time, we don't care about it. All right? Most of the time, we don't. right? Most of the time the world is in steady state. And so it turns out that in steady state, we can simplify and get rid of most of the differential equations. And we saw the reasons for that last time. We're going to review those again here real quick. And then we're going to look at the tool that allows us to sort of bypass that stuff. So the thing that we looked at last time was look at this idea of a phasor. All right, I introduced at the very end this idea of a phasor. And we saw also one other important thing. If I have a sine wave as the input to my circuit, in fact, I'm going to jump ahead and come back to this phasor thing for a second. Let me jump to this. So if I'm looking at what last time I did, 2 simulations, I had this static circuit and then I had an RC circuit. So what I would call a dynamic circuit. So in this case, I said this guy's a voltage divider, right? So if I have a sinusoidal voltage source as my input, and I wanted to look at the voltage across this resistor, right? So that may be a confusing circuit to look at. So if I had this, and I said to you, what's the voltage V out across this guy? And V in was 10 sine 2 pi 100 t. What is going to be, first of all, what is that circuit? What do I call that circuit?
It's a voltage divider.
Voltage divider, right? And so what's going to happen? I mean, what should the voltage across that resistor, that V out, what should it look like?
It should be an attenuated version of the original.
Yeah, beautifully stated. It should be an attenuated version of the original. And attenuated means what?
Decreased.
Decreased in its amplitude, yeah. So it's smaller, it's attenuated. But otherwise, it's still got the same what?
Amplitude?
Different
Frequency.
amplitude. The
Same
amplitude's
frequency.
Same frequency. Yeah, same frequency. That's correct. Yeah. So if I look at it, and the math is here and it's in the notes from last time. Basically, what I'm looking at is this is my input voltage. This is V in. And the red is my output voltage. So this is V out. And then I also plotted the current in that circuit, I of t. All right. So they're all there. So what I see about all of them is they have the same frequency. Their amplitudes are different, but they have the same frequency. What also we said a sine wave or a cosine wave has 3 parameters, right? We've talked about 2 of them so far, right? Amplitude, frequency, and what's the other one?
Period.
Period and
Phase-
frequency are sort of the same thing.
Shift.
Phase
Oh,
shift.
The phase shift.
Phase shift, yeah. So the timing of the waveform, I guess, is sort of set, if you will, by the period or the frequency. They're kind of the same. So there's 3 pieces: the frequency or period, the amplitude, and then the phase shift. So if I looked at this circuit, right? This circuit was a little bit different. Now I replaced that resistor with a capacitor. And I guess before I move on to that, I mean, what's true about the phase shift here between the voltages and the currents? What's true about their phase shift? Is there one?
They're all in phase together. There's no phase shift.
They're all in phase together. That always happens if I have resistors, and only resistors. That always happens. Now we looked at this circuit here, right? And we called this V out. And we go through, and I called this V in, and we wrote a differential equation from KVL. I don't want to go do that now, but it's going to become V in equals RC dV out by dt plus V out, right? And so that guy has a transient response, which is A e to the negative t over RC plus B cosine omega t plus phi. No reason why I have to pick cosine rather than sine, but we do, all right? And again, for reasons that we're going to see a little bit more about. So basically, this is my steady state solution here. In general, we say it has a different amplitude than the input. So this input is my V in. It's got a different amplitude and a different shift. And what we saw with this is the transient solution was here in this particular case. And I changed the frequency. So in this case, the transient solution is gone very quickly. The transient solution went to 0. So the thing to remember is this is A e to the negative t over RC plus the steady state. The thing to remember is this is maybe a little bit confusing. This guy is going to 0 while this is also happening. The total, you never look at just the transient response. One thing that might be confusing is I'm circling this and calling this the transient response. It's really the transient plus the steady state together because they both happen together. It just so happens that this guy is just doing his normal thing while this guy is going to 0. All right. And so it's hard, you don't see it going to zero, but its impact is effectively going to zero. And you can kind of think about that because this guy right here, if you look at the total solution, it's at zero, right? If I had cosine is clearly not zero at t equal to zero. It's the effect of that a e to the negative t over rc, which is screwing things up.
So the reason we care about steady state instead of transient is because transient goes to zero really quickly, and it's irrelevant in like applications.
Transient's relevant. Transient's relevant in some applications, right? And I'm not suggesting that it's not. It's just that the majority of the time we're just worried about steady state, which is really where you spend most of your operating time. Think about the power grid. Power grid's on and working, right? When I turn a new load on, there's a transient that happens. The transients really, to be honest, the way I always thought about this, or the way it was always explained to me, and I've seen this play out in my career, is that the guys who understand transient conditions usually make the most money because that's where the problems happen. All right. And so usually that's where, but the majority of our time is focused on steady state because that's really where, if I'm thinking about operating the power grid, for instance, it's in steady state. And so understanding steady state allows us to make the math a lot simpler. And we only need to focus on the more complicated stuff in those cases when there's a problem, when there's something different than steady state that we need to be worried about. Hopefully that answered your question.
That makes sense.
Yeah. It's not to say that transient doesn't matter. It's just that it's because it's a short time condition, it doesn't matter as much. Certain cases we got to think about it. All right. If I'm looking at this picture though, most of the time I'm in steady state. So I'm looking at the input voltage and the output voltage, the voltage across that capacitor. And I said that the sine wave I've got has a frequency of 0.1 hertz. Okay. What would you say about the two voltages here? So just to be clear, right? V in is here. Here's R, here's C, and here's V out. V in and V out are different from each other, right? And just in general, right? They're one is across the capacitor, one's across the source. In this case, though, with the V in being, what did I say? It's in this case it is cosine 2 pi ft. Okay, F is 0.1 hertz. What's true about those two voltages right there, the V out and V in, once I get to steady state? How would you describe them?
They should be equal.
They're pretty much equal. Yeah. In other words, they same amplitude and same phase shift. This case here, once I get to steady state at 10 hertz. So what I did is I took this F here and I increased the F from 0.1 to 10. What do you notice there?
They're not in phase anymore.
Phase shift. The phase shift is clear.
Yeah, phase shift, and it's also attenuated, right? The amplitude has changed. There's a shift and a scaling, right? And then I jacked it up to 1,000 hertz, right? And then when I do that, it's almost as if, this guy is really starting to get pretty tiny now at this point. It's almost disappearing, okay? Which is important. I can actually make stuff almost disappear if I change the frequency and I play with the values properly. So essentially, just to summarize for this, right? What I see is, in this circuit, at least for this circuit, when the frequency was 0.1, input and capacitor voltage basically the same. 10 hertz, they started to shift a little bit, right? And then by 1,000 hertz, they're really shifted, right? Like in this case, yes, it's smaller. But how much phase shift does it look like? It's hard to tell. Here's the peak, right, of that red waveform right there. He looks like he's peaking right at the point where the blue, the input, is going through zero. How much phase shift is that? How many degrees of shift?
Minimal.
Well, so let's draw this picture here. So here's
90.
90. Yeah, I heard somebody say it, right? If one waveform is going through zero while the other one is peaking, then the shift between those peaks is about 90 degrees, right? Think about sine and cosine. They're 90 degrees apart from each other. All right, we're going to deal with that in a little bit. But those guys look like they're 90 degrees out of phase with each other. If I follow that? I'm exploiting your knowledge of the sine of theta function. All right. So basically summarizing all of this, all right. Essentially, if I have a circuit with only resistors, the frequency of the currents and voltages in the circuit are all the same, phase is the same, amplitudes are different, right? Phase and frequency all the same. If I have capacitors and inductors, still the case of the frequency is the same, but the phase might change and the amplitude might change, right? So what that means is that the sines and cosine waves that we have might be shifted left or right from each other, or scaled bigger or smaller, but they're still the same frequency, okay? And they're still sinusoidal. I can't put a square wave in, well, I can't put a sine wave in and get a different kind of waveform out. All right, if I put a sine wave in, I'm getting sine waves out, okay? So basically that kind of begs the question, we have all this fancy math that goes on, when it comes to differential equations, but it would appear, looking at just that summary, that there's got to be a way to simplify this and avoid the differential equation, and there is, all right? And that requires us to go back to what we introduced at the end of class last time, which was this concept of something I called a phasor, okay? So let me go back to my earlier slide here and review this idea of a phasor. So this guy right here is in particular a voltage, and I said my general form for any kind of sinusoidal waveform is going to be referenced to cosine, all right? And I want to figure out the values here. So in this particular case, I have, I don't know, V of t, it's a voltage, and it's equal to, let's say, V cosine omega t plus phi. And I want you guys to help me out here. What are the values V, omega, and phi? So let's start with the easy one here. Let's start with the amplitude. What is V in this case?
The difference between two peaks.
Not the distance between two peaks, but the amplitude. It's the
It's
peak
going to be
value.
10.
10. Yep. So V is 10. All right. Now, if you go into the lab, if you guys ever actually do that, right, what you'll find is that the function generator might tell you the peak to peak value. All right. But the number that's written in front of here is the peak value. All right. So 10.
So it's always going to be the peak, the value of V?
Well, because it's a definition, right? Cosine of phi. What's the maximum value of cosine of phi?
1.
1, or cosine of theta, right? So if it has a peak value of 2, 2 times cosine of theta can now vary between 2 and minus 2, right? Or in this case, 10 cosine theta can vary between minus 10 and 10. That number in the front, just mathematically, has to be the coefficient that makes it bigger or smaller, right?
Okay.
So it is between the minus 10 to the 10, like the.
Well, if I have 10 cosine theta, it is, right? But by definition, if I have cosine theta, that's between 1 and minus 1, right?
Yes.
If I have, V times cosine theta, then it's between V and minus V.
I got it.
Right. Yeah, you can just think of that as an inequality and multiply everything by the same thing, right? So in this case, the amplitude is 10. How do I figure out omega here from this picture? Figure out omega.
T is 0.
You find the frequency, and then
Yeah, how do I find the frequency?
Oh,
Finding the frequency is hard. What do I want to find instead of the frequency?
the period.
Period.
1 over omega or something?
Well, I want to
gotta
find the
find delta
the
T.
period. Yeah. So the period. What's the easiest way to find the period?
From each peak.
The distance
each
between two
peak.
peaks.
Yeah, distance between peaks or distance between zero crossings. Basically, right. So this is T like that. All right. So that's my period right there, T. And again, hard to see that maybe without me giving you numbers on it, but that T value there is, what's it look like it's about? Anybody tell?
Excuse me, sir.
0.9.
Yeah, it's like 0.1 seconds.
0.1.
Yeah, about 0.1. So, all right, now how do I relate that to omega?
2 pi over the peak? I mean, 2 pi over the period.
Yeah, right. Yeah, that's exactly right. F is 1 over t, all right, which is 10 hertz. And omega is 2 pi f, or 2 pi over t, like you just said, which works out to be 2 pi times 10, like that. All right. So whatever that is, 20 pi, whatever number that works out to be. All right. What are the units on that guy?
Radians per
per
second.
second.
Radians per second. That's right. All right. Now I don't want to get too bogged down in this now, but how do I, so once I know that, how would I figure out phi, the phase shift?
Omega times delta t.
Yeah, an omega times a delta t. Yeah, in this case, you know, I don't have a delta t per se in this case. I would look at this. I have to find probably the value at a particular time. So I would have to say, in this case,
0.
yeah, let's say v is 0. Let's say I know what that is. And I know what this is. I plotted it, right? So it's 7.07. Okay. And I chose that on purpose. 7.07 is equal to 10 cosine 2 pi 10 t plus phi, right? And I guess to be really clear about this, I'll do it the way your calculator would do it. It's 10 over the square root of 2, right? Is what it really is. All right. So if I'm looking at that right there, if I plug in t equal to 0, right, to this, what happens to this expression if I plug in t equal to 0?
It goes to 0.
Yeah, 2 pi 10 t does, right? But the argument doesn't, right? I become 10 cosine phi, right? So then you basically say, well, what's phi equal to? Right? So phi, if you do that, put that in your calculator, you see phi equals 45 degrees. Okay? Or pi over 4 radians. So I could say pi over 4 radians. Again, like I said, I don't ever use radians, and you'll never hear any real engineer say radians. It's more of a math thing. So I always use degrees. Okay. You guys see what I did there?
Is there any particular reason that you wrote 2 pi 10 t, or could you just write 20 pi t?
I could write 20 pi t, but the reason you know what, I always write that. You'll always see me do that. And the reason I do that is because, just like I said, no real engineer ever uses radians. Nobody ever says, oh, that's, 348 radians per second. If you talk to somebody at Duke, they'll say, it's a 60 hertz or it's a kilohertz or what. So they talk in terms of F.
So it's easier to find the frequency because it's just 2 pi f and you have 2 pi 10 there.
Yeah, and we, like I said, we always talk in terms of F. Like, for instance, you have a computer that has a 1 gigahertz clock, all right, let's say, or a 2 gigahertz clock. Nobody ever says that it's 628 gigaradians per second, right? So we use F just a lot more. And so I tend to write it that way just because we use F more. Okay. Good question, though. It's just my thing. Sorry. So what I did was I defined this thing called a phasor. Right. So the phasor basically said, you know what? I don't really need to know. Once I know that I'm operating at a particular frequency, what I do is I create this thing called a phasor, which is a complex number. And again, we're going to see why we do that here in a second. But this guy is basically its complex number, and I write it as whatever the amplitude is, and then whatever the angle is. All right. And so we do that in a complex plane. So in a complex plane, this is the real part. This is the imaginary part here. Right. So you guys know, you've been talking about this with Yahoo over in 2254. For this waveform that I drew out here, which is apparently 10. So we figured out that this guy was 10 cosine 2 pi 10 t plus 45 degrees. What's the phasor for that guy?
10 angle 45.
Yep. So this guy has, so V equals 10 angle 45 degrees. And I would draw that right here.
So as a complex number, that would be 10e to the j times 45.
Not quite. We're going to get to that point. This is effectively a way to write complex numbers. 10 angle 45. That is it. That is the polar format of a complex number, right? So let me jump over here a little bit. I'm going to get to the question that you just asked there, right? If I'm looking at this guy, 10 cosine 2 pi 60t minus 90, what would be the phasor for that?
10 angle negative 90 degrees.
Yeah, 10 with an angle of negative 90 degrees. Okay. Now that's a complex number. And so what's the other way I can write that complex number? All right, that's polar form here.
10 cosine negative 90 plus 10 sine negative 90.
Yep, 10 cosine minus 90 plus j times 10 sine negative 90. So in this particular case, what's that going to simplify to? Anybody know?
Do you want it in the E form or do you want it?
All right, good. So you guys are learning that with Yahoo too. The Euler's identity. I just, in this case, just evaluate that for me.
Negative 10j.
Yeah, negative 10j. All right, is how I can write that. So this is my rectangular form here. And yeah, the other form we can use is the Euler identity. I'm not going to do that with you guys because that's, I like that. It's the way to do it, to be perfectly honest with you, but I don't do it. That's more a 2254 thing. How would I do that?
Well, the
0
identity
minus
for
10j.
cosine.
Yeah, this guy would be 10e to the j 90 degrees if I wanted to go that direction in the complex exponential format. You guys have seen that with Yahoo now?
Yeah.
Yeah.
All right. Yeah. All right. I'm not going to use that pretty much. I'm going to use usually this guy. All right, because it captures everything that we need to understand here. I don't want to make the math needlessly. Not to say that it's hard, but you guys get lost in math easily, and I want to make sure that we keep the focus on the things we really need to focus on. Now, if I have 5 sine 2 pi 30t plus 30 degrees, that one's trickier, right? So basically, what if I have a sine wave? All right, so first of all, the red and the blue here, which one's sine and which one's cosine?
The blue is the sine.
Blue is the sine, yes. This guy is sine omega t. Okay. So let me ask you this. The red one then is cosine, right?
Yep.
What do I need to do to cosine here? So what do I need to do to my cosine to turn it into sine?
Shift it left.
Shift it left. And how many degrees do I need to shift it?
90.
90. I need to shift it left 90. So the way I look at this is that says cosine omega t. If I shifted it 90 degrees to the left, sorry, am I doing that right? No, 90 degrees to the right. Yes.
Yeah.
I pull this guy 90 degrees to the right. That is the same as sine of omega t. Look, I just derived, by looking at a picture, I just derived a trig identity, right? That is a trig identity. You can go and find it online, and just Google trig identities. But, in my mind, I can picture very easily how I can move a cosine and turn it into a sine, okay? So let's say I had this. Let's say I had sine omega t plus some phase shift. What would I need to do to turn that into a cosine, do you think?
Add 90.
Well, what would it be? Not add 90.
Oh, sorry, yeah.
Do what?
Subtract 90. Subtract
Yeah,
90.
same thing. Cosine omega t plus phi minus 90. Like that, right? Same thing, okay? So what it says is if I have a sine, a sine is always a cosine shifted minus 90. Question I always ask myself is when I see sine, is what would I have to have done to its cosine companion to turn it into sine? Well, I would have had to take that cosine companion and move it to the right 90 degrees. Okay, you can always look up the trig identity for that, right? But it's fairly easy to remember it. So if I gave you 5 sine 2 pi 30t plus 30 degrees, what would that be if I had to give a phasor for that?
5 sine 2 pi 30t minus 90 plus 30.
Well, yeah, you could do it that way. Yeah, so so that's equivalent to 5 cosine 2 pi 30t plus 30 degrees minus 90 degrees. So what's that phasor wise? What's that equal to?
Negative 60.
Yeah, 5 with an angle of negative 60. All right. So we're going to use that often. Important thing is, in the real world, if I go to an oscilloscope, right, and I use this, I'd say this in 2254 if you guys had it with me. If I stuck my hand in a wall socket right now, which I don't recommend that you do, but you could. If you use one hand and it's a nice wall socket, you could stick your hand in there and you would feel it. You'd feel a pulsation at 60 hertz in your hand. Don't do it, and don't say I said to do it, right? But if you did that, you'd feel it, and I have, so I know this, right? You'll feel that pulsation at 60 hertz, right? The important thing is there is this sort of up and down voltage that's happening right there. What I'm saying is once I know what the frequency is, I don't really care about the details of that waveform. What I care about is this phasor idea. Okay, we're going to go into that now, right? But if I just keep track of the angle and the amplitude as I work through the circuit, then I can really make the math a lot easier. The thing that's weird about this is that means that I basically just did something strange in that I said, you know what, we're going to start using complex numbers, right? We're going to start using imaginary numbers, which is weird because imaginary numbers are by their very name imaginary, right? So I go into a weird domain of math to get rid of a really, really annoying form of math, which is differential equations. All right, so I sacrifice weird for difficult, and for whatever reason, you know, I think we all agree that weird seems better than difficult. All right, if I had to summarize it, weird is better than difficult, and that's basically why we go to complex numbers, and we're going to see why here in a second, because I can get rid of the differential equations and basically go back to Ohm's law. All right, any questions? Many.
So do we always, in order to use like that phasor, it has to be always in cosine for us to just say, take amplitude, take the angle?
Yeah,
Okay.
so that's the kind of thing like on a test or something like that. I'm going to give you sine because I know that, you know, a quarter of you guys will forget that.
Okay.
Right.
Yep.
It's
Now we decide
always,
on.
yeah, it's always reference to cosine. Yeah. All right. All right. So we talked through this here. Now I want to get to the why of this. All right. So let's look at how we would analyze a circuit here. So let's say I got a voltage source here. I don't know. Right. And I put a voltage source across this guy. My voltage source was, I don't know, V cosine omega t plus phi. Like that. Right. And I gave you that circuit. What would I of t be?
VT divided by R.
Yeah, V of t divided by R. Right. So what does that become? Well, V over R, the amplitude's different. Do I change anything about that cosine?
No.
Nope. It's cosine omega t plus phi. Okay. So let's go ahead and let's say, all right, well, if I gave you that, so V of t was this. What's the phasor for V of t? How would I write that? I'm going to write it as V under bar. I always put this under bar for my,
Under bar phi,
it'd be what?
the angle.
Yeah, so it's got an angle, it's a magnitude of V, whatever that is, just a number.
A little, I don't know what you call, looks like a less than sign.
Angle phi.
Yeah, it's the angle sign is what I call it. Yeah. V angle phi. All right. What about I here?
Is V over R angle phi?
Yeah, V over R with an angle of phi. And I'm going to write this as, if I look at this for a second, so V is equal to V angle phi. Okay. And if I looked at this, I could also say, if I move the R over, right, couldn't I write R times I like that is equal to V angle phi, right?
Why
I
not?
just multiply both sides by r right here.
Yes.
So this guy is the phasor, V. So the V angle phi, the thing to remember is that is a number. V angle phi is a number. It's a complex number. So it's the polar notation for that. I have V the phasor equals I the phasor times R. That looks pretty familiar, doesn't it? It's Ohm's law.
Ohm's law.
Yeah. V the phasor equals I the phasor times R. This is Ohm's law. All right. And so this is not particularly nothing fancy about this right now, right? What I just found was I can relate the phasors. Well, no, I can also say V of t equals I of t times R. All right. Nothing fancy about that. Well, it's going to get fancier in a second when I bring in the capacitors and inductors. Okay. So what that says is no matter what the voltage is, as we already saw, the voltage and the current time aligned with each other. All right. And what do I know about what's if they're time aligned with each other like that? I see that the magnitude. So these phasors are complex numbers. So there's two equations that go with them. If I look at the magnitude here, I see that basically if I have a phasor and write it like this, the magnitude of that phasor is always equal to the magnitude of the current phasor times R. Right? The magnitude here, this is the amplitude of the sine wave. Okay? And this is an amplitude of the sine wave. Okay? So if this guy had a peak value of 5 and this guy had a peak value of 10, this would be 5 and this would be 10. Okay? What's true about their angles?
They're the same?
Yep. So the way I write that is the angle of V is equal to the angle of I. All right. So again, the way I'm saying this here is V, my phasor, has a general magnitude like that and an angle like that. Okay. And I, my general phasor, has a magnitude and an angle like that. Okay. All right. Nothing fancy about this. Right. So the fancy way of stating something we already know, which is to say that Ohm's law is the thing. Okay. But when I get to a capacitor, it gets trickier, right? So I've written out here I equals C dV dt. So let's say I had this. Let's say I put a voltage on here, okay, like this. All right. And let's say that voltage source is equal to V cosine omega t. All right. What would be the phasor for this guy?
Just V angle 0?
Yep. I could just say V. He's got an angle of 0 degrees. Okay. Angle 0 degrees. Okay. So how do I figure out the current in that capacitor?
You have to take the capacitance into phasor form.
Well, the capacitor is just a thing, right? A capacitor is not in phasor form.
Just take the derivative of the voltage.
Take the derivative of the voltage.
Yeah.
Yeah. Right. So I can say I of t equals C dV dt. All right. So that's C times d by dt of V cosine omega t. All right. So help me out with that. What's the derivative of V cosine omega t with respect to time?
Negative omega.
Negative omega.
Negative omega V sine omega t.
Yep. That's right. Like that. All right. So what I want to do though is I said I don't like sine, right? I want to get rid of sines and I want to change them over to cosines, right? That's just a definition that we're working with, right? So how do I turn that sine into a cosine again? What did I say I needed to do to turn sine into cosine?
Do cos omega t minus 90?
Yeah. Okay. Okay, like that. Now, if I'm going to come back and do this again here in a second, assuming I had maybe a phase shift in that. But if I let's now tell me that. So I do my phasor for this. What is my phasor now for I?
Negative omega CV angle negative 90.
angle negative 90. Yeah, that's right. So looking at that, I see that and I guess maybe I can, there's a couple of ways of me thinking about this, but if I wanted to relate these guys together, all right, let's write this over here. So V was equal to V angle 0 degrees. I was equal to negative omega C V angle negative 90 degrees. Okay. So if I look at this here, right? So let's just draw the waveforms here for a second, right? So if I'm thinking about this here, first of all, this angle negative 90 degrees. I got this minus sign out here, and I got an angle of minus 90 degrees. Okay, that's weird because when we use polar notation, I put the magnitude in the front. What's always true about the magnitude? What kind of number is magnitude always supposed to be?
Positive.
Positive, right? If I have a minus sign, if I have the number -1, that has an angle, doesn't it? Okay, has a magnitude of 1, right? What's his angle?
Negative 90 degrees. Or
where is -1 in the complex plane?
180.
On the left side.
It's over here, right? So what's his angle?
0.
180.
Oh,
180. Okay, 180. So that means that in reality here, what I actually have, so that minus sign right there is also the same as 180 degrees, right? So this guy is also omega CV angle 90 degrees, right? You guys follow that?
No. Can you read?
Wouldn't negative 90 just be
So-
clockwise?
So if I have -1 times a number that has 3 angles, just use numbers, right? 3 angle negative 90 degrees. If I multiply two complex numbers like that, right? This guy, what I'm saying is this is the same as 1 times angle 180 degrees times 3 angle negative 90 degrees, right? Follow what I just did there? Just from
so
one
do
line
they
to the next there.
do those angles follow the exponent rule? Since
Well,
you're adding.
they do when I'm using Euler. I'm trying to stay away from Euler.
Okay.
I'm proud that you remember that from 2254.
I do.
Well. Yeah. All right. 1 angle 180 times 3 angle negative 90. All right. So if I follow those together, if I multiply two complex numbers, what do you know about how do I figure out the magnitude when I multiply two complex numbers?
You got to do the square root of the real.
That's when you figure out the magnitude of one number, right?
you just multiply them together.
Yeah. When I figure out if I have two complex numbers, I multiply them together. Have you seen that with Yahoo yet?
I think we just took that like
Yeah.
a day ago.
Okay. All right. So you're going to see it. So this is like, 2 80 sitcoms that are related to each other here, right? So we're going to start talking about a lot of the same sorts of things here. So in this case, I got polar number times polar number. I multiply their magnitudes. So in this case, 1 times 3 would be 3. And what do I do to their angles?
You add them together.
I add them together. So it
Add them
becomes,
together.
yeah, negative 90 degrees, positive 90
Positive.
degrees. Yeah. Okay. Again, you're going to see more and more of that with Yahoo. All right. I mean, there's a reason why you're taking 2254. It doesn't just totally come out of the blue. The math there is very common. All right. We use it a lot. So there's a reason why you do it. But what that says, I want to plot these guys in a complex plane here. Okay. All right. So here's the real and here's the imaginary. Okay. So this sort of says, if I'm looking at this complex plane, where would I draw the voltage vector? The voltage phasor. Where would I draw this guy?
Just on the
Along the real axis.
Yeah. So here's V. Where would be I?
Imaginary.
It would be on the imaginary and would up or down?
Up.
Up. All right, so here's I. What's the angle between them?
90.
90. Okay. So what I see in this particular case is there's always a shift of 90 degrees between current and voltage. And current is always 90 degrees ahead. So let's actually look at let's take this situation a little bit further. So let's say I had a different voltage source. Let's say V of t was V cosine omega t plus phi, right? And if I look at that, right, what's the phasor for this guy? What's his phasor? B.
V angle, whatever that.
Whatever
theta
phi.
is.
Yeah, whatever that value is, right? So if I did, okay, well now keep it the same. I of t equals c dv dt. So c times d by dt of voltage cosine omega t plus phi. All right, help me out. What's the derivative of that? What's the difference here? What's the derivative? How does the derivative change?
Negative.
We have to include the plus phi in, but it doesn't change the product.
Doesn't change the result. Yep, that's
Yeah.
right. Yeah, so it becomes negative omega c v times sine of what?
Omega t plus phi.
Omega t plus phi. That's right. Which, if I convert that into his companion cosine there, it'd be cosine what? Omega t plus phi, then what?
Minus
Minus
90.
90.
Minus 90. Okay. So let's phasorize this guy. So we'll say that is what? What's his magnitude? So in front, I'm going to say I got negative omega CV, right? And then with an angle of apparently phi minus 90 degrees. What do I say? If I multiply by -1, what does that do to the angle?
Both positive.
Makes it plus 90, right? So this guy becomes omega CV, and it says his angle is going to be phi plus 90 degrees. All right. So if I go and look at this picture right here, so what I just said was my voltage phasor was V, and it had an angle of phi. My current phasor, I'm going to say, has some magnitude. What do I do? Some magnitude I. Okay. And the angle was what? What's the angle of this guy? So my current is this. Let's before I go to the next slide, let me read it this way. I is equal to, he's got some magnitude and he's got some angle, right? What is the angle in this case? It's phi plus 90 degrees. Okay. What about I? What's this magnitude? What would I write that as in this case?
Omega c times v.
Omega c times v. Okay. So let's summarize that here. It looks like I have this. All right. And the magnitude of I is omega c times v. Okay. So how would I draw this? All right. So let's give phi a number. People like numbers, right? So phi, let's give that a number, 45 degrees. Okay. So where would that voltage phasor be?
In the first quadrant.
Mm-hmm. All right. So here he is. Here's V. All right. And this angle here is, in general, it's phi. Where would I draw the current?
Second quadrant.
Second quadrant. And how much do I need to turn it from the voltage?
90 degrees.
90 degrees, right? Because its angle, the angle of the current, is 90 degrees on top of the angle of the voltage. So I rotated that guy by 90 degrees. So he's basically going to be over here. Sorry. Right, there's 90 degrees. Crap. Here's I. Right? So basically what I see in this picture is I want to do some relationships here. what's true from this? What appears to be true about the angle of I? I'm going to write it this way. Angle of I and the angle of V. What is the relationship that is always going to exist between those angles?
They're gonna be
They'll be
90
the same.
degrees apart.
They will be 90 degrees apart. And in particular, the angle of the current is 90 degrees ahead of the angle of the voltage. Okay, you guys see that? In other words, this guy, the current, I added 90 degrees to the angle on the voltage. Right, so if that angle of the voltage is 45 degrees, looks like that current's over at 135 degrees. What about the magnitude here? Well, the magnitude of I looks like it's omega C times V. V was the magnitude of the voltage. So it looks like I have omega C times the magnitude of the voltage. So what I just showed there is, okay, if I know the angle of the voltage, I can add 90 degrees to get the angle of the current. If I know the magnitude or the amplitude of the voltage, what do I multiply by to get the magnitude of the current?
Omega C.
Omega C.
Omega C. All right, so there's a way for me of simplifying this, right? So what I can see right now is if I take the phasor of the voltage, okay, and the phasor of the current. So if I just put all these guys together here, right? So angle of current is equal to the angle of the voltage plus 90 degrees. The magnitude of the current is omega C times V. So that says I can basically write this guy as, let's do it this way. I is equal to omega C times the magnitude of the voltage, right? This is the magnitude of it. And the angle of it is always the angle of I. Well, it's the angle of I, but it's the angle of the voltage plus 90 degrees. Okay. You guys follow what I just wrote there? I'm just saying that this guy is, so in this case, if the angle of the voltage is 45 degrees, this number would be 45 plus 90. That's basically writing this out with complex numbers. Now, here's the thing. If if this is something you probably have seen with Yahoo, if I take, or at least you will see it very soon, right? If I add 90 degrees to something, so if I take the number 3 and I multiply it by 1 with an angle of 90 degrees, okay? 1 with an angle of 90 degrees, if I were to draw where that is in the complex plane, where is that?
It's just
Straight
like
up.
It's straight
axis,
up.
right?
It's straight up, okay? So this result here is basically 3, and let's do it this way. Yeah, let's say I had a different number. Let's say I had 3 angle 45 degrees times 1 angle 90, okay? 1 angle 90 is also the same as what? If he's going straight up like this. Right, did it rectangular form? What would it be in rectangular form?
J.
J. It'd be J, right? It points straight up. And so you could see that by going and saying cosine of 90 plus J sine 90. Right? That's going to equal J. So this guy is the same as 3 angle 45 degrees times J. Okay? So anytime I am basically adding 90 degrees, it is the same as multiplying by J. And so, long story short, that basically tells me this. I can relate these guys like so. The phasor of the current is equal to omega C times J times the phasor of the voltage. Okay? You can go through that slowly. It is easier to see it with Euler's identity, right? But you're not fully comfortable with seeing that through Euler's identity just yet. But suffice it to say, when I look at that relationship right there, what I see is, let me just put that in parentheses like that. It looks like I have some relationship here, right? If I bring that over, it looks like I have I times 1 over j omega c is equal to the voltage phasor. You guys
So the-
follow that? What I just did to rearrange that?
Adding by 90 is the same as multiplying by j.
Adding 90 degrees and multiplying by j is the same thing. All right, and I can take that offline to prove that if you want to see that.
I'll take your word for it.
Yeah, I mean, we can look at it right after class if you want to.
Okay.
Right, but assuming that that's true, right? If I look at this statement right here, I mean, basically the fact that I, the phasor, equals j times omega c times v, all I did was some algebra right there, right? So it looks like I have I times something equals the voltage. Everything in this is known before I start a problem. What does that look like?
Ohm's law?
Looks like Ohm's law. I times something that's known about the circuit is equal to the voltage. I call that the impedance. All right, that is the general term that we use when we talk about circuits. It's also a phasor, right? What it tells me right there is that Z, which is what we call it, all right, we don't use R, we call it Z. Z is equal to 1 over j omega c for a capacitor. And what this says is, okay, so if I told you I had 1 over j omega c, that's also the same as negative j times 1 over omega c. All right, I don't want to bake your noodle on that one per se, but again, you can prove that 1 over j is minus j. So that guy is also a phasor. He's a complex number, right? Where is that complex number in the complex plane?
Imaginary.
It's on the imaginary axis. In which way?
Going
To the
down.
left.
Going down. So I can write that as what? 1 over omega c with an angle of what?
Negative 90.
Negative 90. All right. So the timing is right to be going through complex numbers over there with Yahoo, because basically, you know, we're going to, AC circuits is all about complex numbers because, and here's why, right? Now I am using complex numbers, but what did I do? Using complex numbers, what was I able to get rid of?
The differential equations.
Differential equations are gone, right? So I've just generalized. I basically said when I'm looking at circuits, I got to deal with not just when I deal with resistive circuits, all that can happen is magnitudes can change. But because of the fact that magnitudes and angles can change, it just so happens that this idea of complex numbers takes into account magnitudes and angles, right? And so it basically creates a way for me to capture those two things in one equation. And so why are imaginary numbers useful to us? Well, they're useful to us because they allow us to capture magnitude and angle in one equation rather than two, right? And so it becomes a simpler way to sort of capture that behavior, right? And so we like that, all right? Makes the math a lot simpler and ultimately allows us to get rid of differential equations, which are very annoying things, all right? So in general, it is always the case that I equals C dV dt. All right, in general, that's always true. But in this special case of what I call sinusoidal steady state, all right, and I mean that whole thing is one word, not one word, but it's one key thing, sinusoidal steady state. I have to be in steady state and I have to be dealing with sine waves, then this is true. All right, if I'm in transient or if I have something other than a sine wave, that is not a true statement. But as I said in the very beginning of this, sine waves are incredibly common, right? And steady state, we often limit ourselves to considering that because the world is mostly in steady state. It's not going through transient conditions. And so sinusoidal steady state gets a really special place, and thus we have AC circuit analysis, which is based on a generalization of Ohm's law using this thing that we just derived called impedance, okay? So in a lot of ways, today is probably the most important day in the class, right? Because we're sort of introducing this really key concept that we're going to use really until the end of the semester. And really, you'll use it for the rest of your life, I guess. But it's really a very critical concept. And it captures the two things. It captures the magnitude change that happens in this circuit, and it captures the angle change. Complex numbers allow us to put those two things in one equation, and that's what's useful about it.
So do the same principles of second order circuit steady states that we were doing in the homework apply for sinusoidal steady states? Like, does the capacitor act like an open circuit?
Well, Eli, it's a terrific question. All right. Let me ask you this. If I have so in all the second order circuit stuff that you guys are working on right now on the homework, what types of sources did I always have in those circuits?
Constant.
Constant, which is DC.
Mm-hmm.
What's the frequency of a DC signal, DC waveform?
0.
0. Okay.
Doesn't change ever.
Doesn't change ever. So the frequency at DC, this is a great question. Omega is equal to 0. What is the impedance of a capacitor? So I'll write it Z sub C is 1 over omega C, J omega C. What is the impedance of this guy for omega equal to 0?
Infinite.
You can't even define it technically.
It's infinite, right? So think about it. If I had a resistor that had an infinite resistance, what would I call that?
Open circuit.
Open circuit.
It would stop all the current flow.
Yep. So that's completely consistent with what we've said up till now.
Okay.
All right. We just unified those two things in a way. And when I look at an inductor, when omega is equal to 0, I'm going to find that its impedance becomes 0. And if a resistor had 0 resistance,
it becomes a short circuit.
Becomes a short circuit. Yeah. And that becomes a really useful tool for us to be able to use, right? As I can make these approximations that allow me to kind of think through what's going on when I'm using impedance. And in general, you hear engineers talk about impedance all the time instead of resistance. Because if you look at it, what's the impedance of a resistor? I didn't call it that when we looked at a resistor, but what's the impedance of it? Right.
It's going to be R.
R, yeah. V equals I Z. In this case, the impedance of that guy, I say, has a magnitude of R and an angle of 0 degrees. Right. It was purely, we didn't have any reason. We took DC circuits. We had no reason to consider that a complex number, right? It's like when you learn numbers in grade school, right? You didn't give them angles. You didn't need to, right? It's not until later that we begin to use the number system in a broader context. All right. So let's look at that here as an example, right? So here's Vn is that voltage, 4 cosine 2 pi 1000 t, and I've got those values here, okay? Now, what does this mean then? Well, this means that this circuit's actually a voltage divider, and I can simplify analysis quite a bit, okay? I'm not gonna do that just yet. We're gonna look at problems using this in recitation on Friday, but if I look at this guy here, right, and I look at what's actually going on in this circuit, what I know is that VC, what's it going to look like? It's going to have some magnitude. I don't know what that is. If I look just in steady state, it's going to be VC cosine what?
Omega t.
Okay, and what's omega going to be if this is my Vn?
2 pi 1000.
Yeah, 2 pi 1000 t.
Minus.
But yeah, I'm going to say plus. It could be either way. Plus the angle of VC, whatever that is. Right? I don't know what that is. I'm going to call it angle VC. So let's say this guy has a phasor that is got a magnitude V sub C and the angle V sub C. Right? That's going to be his angle. So looking at this, I ran that circuit, did some analysis on this guy, and I found V sub C and I sub C. All right, so I found out what they were. All right, so if I'm looking at this guy, what I see is the y-axis value is the voltage. So in this case, the peak value of that voltage, V sub C, looks like it is, in this particular case, magnitude-wise, looks like it's 0.04, like that. You guys, so 0.04 volts, that's the peak value of this voltage, right? So what I said before is that I equals Z times, oh, forgot Ohm's law. I times Z is equal to V. So I'm going to do it this way, like that. So I said that the impedance of that capacitor is equal to 1 over j omega c. Okay. So this is a true statement if I say, well, okay, well, let's talk about the magnitudes here. All right. Magnitude of I times magnitude of Z is magnitude of the voltage. Okay. So 1 over j omega c. So I got to calculate that here, right? So let's just calculate the impedance of that, or the magnitude of that. What's the magnitude of 1 over j omega c? It's 1 over omega c, isn't it? Right? What I got to do is I got to plug in my numbers there. So 2 pi 1000 is my frequency. And my capacitance was 1 microfarad. So what's 1 microfarad if I write it exponential notation?
-6.
Yeah, 10 to the minus 6. So if you run those numbers there and you calculate what that guy is supposed to be, right? And plug that in. So if I go into this and I put this number into this equation and I put 0.04 into this equation, if you do that math, that magnitude works out to be 2.5 times 10 to the minus 4 amps, or 250 microamps. Okay. Not an uncommon value for a circuit like that. So if I look at the peak value of this, what do I see? It looks like it's about 2.5 microamps. Okay, so it's exactly what I would have expected it to be. All right, so everything is right. Now, what else? What's the other statement here? So there's another part to this whole expression, right? So we said VC, well, I'm not writing, VC, the phasor, is equal to I, the C, the phasor, times the impedance of that capacitor, right? So what was the relationship we saw there? So this is IC times 1 over j omega c. Okay. So if I looked at this, so if I have a complex expression here, complex number A equals complex number B times complex number C, what do I say about their angles? The angle of V sub C is equal to the angle of I sub C plus what?
90 degrees.
Yeah, plus the angle of
Z.
Right? So the angle of Z in this case, if I look at this guy right here, this impedance, what do we say was the angle? If I have 1 over J, that guy has the angle of Z
-90.
is -90. Okay. So that says that this guy is angle of IC minus 90 degrees. Okay. So that says what? What does that mean in terms of the picture that I drew right there?
The peaks and zeros will line up.
The peaks and zeros are going to line up. There's a 90-degree shift between them, right? So what I did was I looked at the peak of the voltage. So when the voltage is at a peak, where's the current? It's at a zero crossing. There's a 90-degree shift between them. And what this says is take the angle of the current and subtract 90 degrees from it, okay? So if I had a sine wave and I said take a sine wave and add -90 to its phase, which direction would I shift it?
To the left.
To the left, right? No, not to the left. If I said shift it -90 like this.
Oh, -90 right side.
Yeah, sorry. I'd pull it to the right. So if I took this guy right here and pulled it over to the right, it would be lined up with the voltage, right? So the current, pull it 90 degrees to the right, and I would get the same thing. So I used the term the other day for this, right? Looks like current has its peak 90 degrees before voltage does. If it has its 90, it's before, because this is time right here, right? If he has his peak 90 degrees earlier in time, what do I say about the current?
Leading.
It leads. Yeah. And there's a term people sometimes use for this, but basically we say that current leads the voltage. Okay. Now I can go through a similar analysis, and I have it in the notes and you can look at it there in the notes. The notes from today are actually already posted and they're worked through. But if I do this same analysis and I say, let's put a current source into this circuit and go through the same thing, that current source looks like this. Basically, what I'm going to find when I do this is I'm going to find that the voltage on the inductor equals the current in the inductor, phasor-wise, times Z. And I'm going to find that that Z is equal to J omega L. All right. So in this case, J omega L, help me out with that. What's the magnitude of J omega L?
Isn't it 1 over?
R,
It's
Oh,
omega L.
and then the angle would be
Angle would be what?
-90.
Well, think about it. Where's
no, 90, right?
J times
90
Positive
degrees?
90.
Yeah, it'd be pointing up like that, right? So this would be angle of 90 degrees.
So with an inductor, the voltage
Yep.
then lags.
So then I don't even like remembering that stuff. I look at it this way. I say angle of voltage equals angle of current plus the angle of Z, right? I just write that out like that. And the angle of Z is 90 degrees. So that says that if I know the angle of the current, right, I add 90 to it to get to the voltage. So what that says is that the current lags. All right. So in this case, the current was leading the voltage. In this case, the current is lagging the voltage. We don't need to get too worried about those terms, right? So what I'm going to do is I'm just going to try to summarize it down to one thing, right? Which is basically this. What do I need to know? The impedance of a resistor is R. The impedance of a capacitor is 1 over J omega C. The impedance of an inductor is J omega L. And this idea of Ohm's law applies. Anytime I am in this special case of what I call sinusoidal steady state, this impedance concept applies, right? And I can use that equation. What's important about that is if I took a circuit like I had there at the beginning, right, where I have R and C like that, and I say, well, this voltage here is 10 cosine 2t plus 30 degrees, right? So if I gave you 10 cosine 2t plus 30 degrees, what's the phasor for that guy?
10 angle 30 degrees.
10 angle 30 degrees, right? And I said, let's say I want to figure out the current in this circuit. What would the phasor, be? I want to know what, so in other words, the phasor is not a real thing. It's a way of representing a real thing. The real current in that circuit would be a sine wave, right? But if I wanted to think about the phasor that represents that sine wave, it would be the voltage 10 angle 30 degrees divided by what? Do you think?
The impedance.
Yep, R plus the impedance, the capacitor. That's where we're going with this. All right, that's how we're gonna use this. Because now I can basically use all the tricks that you learned, nodal analysis, mesh analysis, all that stuff. I can use all of that to figure out what the voltages are in that circuit, and I don't need to do anything with differential equations. Okay, use all the same techniques.
That's definitely a lot better.
It's a lot better. Yeah, there's no doubt. It's weirder because we're dealing with complex numbers, but it's a lot simpler to deal with. Okay.
So in this case, though, R is okay. I see. Never mind.
So can you go back to the slide where we're talking about the impedance of the inductor?
Yeah.
I swear there are the nodes. Oh, okay. Okay, I can deal with that.
Yeah, and I mean the derivation of this is in the notes, right? If you, I mean, again, it's the same kind of derivation, right? If I have a current that looks like this, I say VL equals L d by dt of the current, right?
Mm-hmm.
Then if I go through that process, I'm gonna see that it becomes, negative omega L times I sine of omega t plus phi. Go through that process, right? And I can say, okay, give me a phasor for that. Well, it would be negative omega L with an angle negative omega Li with an angle of phi and blah, blah, blah. Go through that same process. And I'll find the same result. All right. All right. So we're done. We're past time. So you guys, I'll stick around here for a couple more minutes if you guys got questions.
Is the office hour today?
The office hours, yeah, I will do my office hours tonight at 7:30.
I have a question.
Yeah.
Is there any like you said that this is like a method for like without using differential equations. So doesn't that mean that like the differential equations method isn't necessary, like isn't really necessary ever, or?
That is an excellent question. It doesn't. It means that it's not necessary if so specifically, I've made a very important caveat to this. This approach is used to figure out the steady state solution when I have sinusoidal sources, okay? If I only care about the steady state solution when I have sinusoidal sources, I can use impedance. That just so happens to be a really important thing. Because like I said, we have sine waves in audio circuits and in power circuits and radio, so all these places it comes into play. But that's not to say that the differential equation is not important. Like if I have DC inputs and I want to figure out what the transient response is, then I have to do it.
Okay.
Now you may say, well, why do you care about that? Well, that actually turns out to be relatively common, right? Like in digital circuits, that happens all the time. That in digital circuits, we actually do have transient responses sometimes that are problematic, and we need to understand that stuff. It's the reason we do it the way we do it is because the physics, if you look at stuff from a physics perspective, you get the differential equations, and then we can just make some simplifications in that special case of what we call sinusoidal steady state.
Okay. Thank you.
Yep. All right.